let's jump right in with an example. Let's express vector 7, 9 as a linear combination of vectors 1, 2, and negative 5, negative 5. All right, so let's use the definition of linear combinations. That means if vector 7, 9 is a linear combination of those other two vectors, then vector 7, 9 is going to be equal to some scalar, let's call it a1, times vector 1, 2, 1, 2, there we go, plus another scalar, let's call it a2, times vector negative 5, negative 5. So if I could figure out what a1 and a2 are, I'm done. I would have expressed vector 7, 9 as a linear combination of these other two vectors. But I need to figure out the values of a1 and a2. Okay? So to kind of think about how we could do this, let's start by just doing the vector arithmetic on the right-hand side of this equation. So I'll leave the left-hand side the same. And if we do the scalar multiplication, the vector addition on the right-hand side, then we're going to get, for our first component, 1 times a1 plus negative 5 times a2. So 1 times a1 plus negative 5 times a2, that's a1 minus 5a2. And for our second component, 2a1 minus 5a2. Okay? Now, I'm going to actually break this apart. I'm going to equate the corresponding components. So if I equate the first component, the vector on the left side of the equation, with the first component and the vector on the right side of the equation, I get 7 equals a1 minus 5a2. And if I equate the second component on the left with the second component on the right, I get 9 equals 2a1 minus 5a2. And so we actually get a system of equations where the variables are the scalar values of our linear combination, a1 and a2. So if I could solve this system of linear equations, I have my answer. All right? So to solve the system, I'm going to express the system as an augmented matrix. The coefficient matrix are just the coefficients on the variable side of the equation. So I get 1, negative 5, 2, negative 5. And then the augmented part is 7, 9. And now to solve this, we want to get this into reduced row echelon form. To do that, I'm going to go use our computer. So let's get our coefficient matrix. I'll call it A. So first row is 1, negative 5, and include the augmented part also, 7. And the second row is 2, negative 5, and the augmented part is 9. So I've got matrix A, and I want to tell the computer to find the reduced row echelon form of matrix A. So A dot RREF, reduced row echelon form. And then to make it pretty, I'll do pprint. Pretty print. That'll make it so that it looks good once I print it. Okay? And so the matrix here, the matrix on the left here, is my reduced row echelon form of the matrix. So it's 1, 0, 2 in the first row and 0, 1, negative 1 in the second row. So finding the reduced row echelon form, we get 1, 0, 2 and 0, 1, negative 1. And notice, I should note that, this is the matrix that the computer gave us. Okay, there's no mechanism to tell it which part is augmented, which part's not. So you just have to remember that that last column is the augmented part of the matrix. Okay? And so we can use this to find our answer. Remember, column 1 corresponded to the scalar variable a1. Column 2 corresponded to a2. So if I look at my equations, from row 2, I get a2 equals -1. From row 1, I get a1 equals 2. And so now I could combine that with this up here to get my final answer. Let's do that. I'll just pull it up here so we could see everything. So 7, 9 is equal to a1, which we found was 2, times vector 1, 2, plus a2, which we found was -1. So I'll actually go -1 times vector -5, -5. And now I have expressed this vector as a linear combination of these other two vectors.